Physics is full of some really deep mysteries. But one of the most fundamental ones is actually one of the simplest to ask. It's a question about the very stuff that makes up, well, everything. Where does mass actually come from? Think about that number, 1,836. Why that specifically? Why not 100 or 10,000? It's one of those fundamental numbers of the universe that has had physicists scratching their heads for decades. And what's kind of wild, or maybe a little bit frustrating, is that our best theory of physics, the Standard Model, has no way to predict this number. Sure, it tells us how particles get mass, something to do with the Higgs field, but it can't tell us why they have the specific masses they do. Physicists literally have to measure these values in experiments and then just plug them into the equations by hand. But what if there was another way to get there? Well, a recent paper is proposing a completely new idea. It's a framework called relator theory, and it tries to calculate these fundamental numbers from scratch, from a totally new underlying principle. So the core idea here is that our reality, our 3D space, is connected to this hidden internal generator space. A good way to think about it is like a shadow on a wall. The physics we see and measure, that's the shadow. But the shadow's properties are actually determined by the real object casting it and the rules governing that deeper, hidden space. And at the absolute heart of this theory is a single, incredibly simple equation called the luminal lock. It says R omega equals C. Now, the R and the omega here basically describe the geometry of that hidden space. Think of them as a kind of radius and a rotational speed. And of course, C is the speed of light. This one little equation acts like a master rule, locking the geometry of that hidden space to the one universal constant we all know. Okay, so that's the theory. But a theory is only as good as its predictions, right? So the author of this paper did something incredibly ambitious. They tried to build a proton using just this one rule. And this is where it gets really interesting. The theory imagines a proton not as a little bag of quarks, but as this stable three-loop bouquet that exists in that hidden generator space. And these loops are locked together in this perfect harmony. The analogy the paper uses is great. It's like three musicians playing a perfectly stable chord, where each note is offset by 120 degrees. It's this Z3 phase lock, as they call it, that creates an incredibly stable structure. Now here is the most important part. The author, Mehrdad Pajuhaan, is very clear about this. He's saying, look, this calculation is from the ground up. There are no fudge factors. He's not plugging in known values or tweaking numbers to get the answer he wants. He just took his three-loop model and applied that one fundamental rule. So, what happens when you do the math? What does this beautifully simple geometric model actually predict for the proton-to-electron mass ratio? The calculation spits out this number, just this, derived purely from the geometry of those three locked loops and the theory's one single rule. And this is the moment of truth. When you put that predicted number next to the most precise experimental measurement we have, the official CODA data value, they are just astonishingly close. The difference is a tiny 0.04%. To get a number this fundamental, this close to reality, from a theory with zero fine-tuning, well, that's the kind of result that makes physicists sit up and pay very, very close attention. But that's also the kind of result that demands some serious skepticism, right? How do we know this isn't just some bizarre lucky coincidence? Well, the author tested for that. They ran the same calculation for other simple loop structures. A two-loop structure, it predicts a mass ratio of exactly 1. In other words, an electron. Makes sense. But look what happens with 4 or 5 loops. The predicted masses just explode into these astronomically large numbers, nothing like anything we see in our universe. This really suggests that the three-loop case isn't a random fluke. It seems to be a special, stable configuration that just happens to land right where the proton is. Of course, we have to pump the brakes a little bit. This is not a closed case. A remarkable result like this always comes with its own set of critical assumptions and some pretty big questions. It's really important to separate what's been shown from what's still just an idea. The entire calculation really rests on 3 big pillars. First, it assumes the theory's starting point for the electron is correct. Second, it assumes that this 3-loop bouquet is a legitimate way to model a proton. And third, that certain other constants of nature carry over perfectly from the electron model to the proton one. If any of those are wrong, the whole thing could be off. And what about that tiny 0.04% error? Far from being a flaw, that could actually be a clue. The paper suggests this small difference might be pointing toward finer details that this simple model doesn't include yet, like the exact shape of the junction or the thickness of the loops. So in the end, this isn't the final answer. It's a really tantalizing first step. The next big challenge for relator theory is to go further. Can this exact same model predict the proton's other known properties, like its magnetic field or its physical size? Answering those questions will be the true test of whether this is just a stunning numerical coincidence or just maybe the beginning of a profound new understanding of where mass itself comes from.